Okay, so let's start. Welcome to this webinar about QF test and image checks. Here on the right on my screen you can see QF test, you already know. On the left you can see a Microsoft Internet Explorer on the top and a Microsoft Edge here on the bottom. Both showing the exactly same website. In this case, it's our own website about QFS and QF test. And I will cover a few examples for image checks and what to do and what not to do, and a little bit about scripting and about image manipulations. So let's start. As you already know, you can simply record an image check here via right-clicking on a component, opening the helper menu and select image here. And if you stop, you get a recorded image of this component. I already did this here for Internet Explorer and also here for Microsoft Edge. And if I replay them, they should work. They show finished, no errors here at the bottom. And also for Microsoft Edge, running, finished, no errors. What did I check? I verified our QF test logo. I checked this little flow diagram. I checked only a part of the logo here, this little Q icon here on top. You can select whatever you want to check. We are clicking here, pressing OK, and then QF test will only verify the marked part here. And I also cropped this image, selected an offset here to verify only this part. Nothing special here. Okay, so now I recorded this check on Microsoft Internet Explorer here on the top, and I'm now trying to replay these checks on Microsoft Edge. And they will fail. The run log tells that these images do not match. However, if I look closely, a human being may think these images are identical, but they are not. What are the differences? If you watch here on the top, where my mouse cursor is now, you will see the coordinates and the color values in red, green, and blue. For example, here it's 18, 42, 81 against 17, 41, 7F. So there are very little deviations in the blue. Of course, these images are not identical then. You can also see here anti-aliasing effects. For example, here on the left of the E, this color here is a little bit more bluish than here on the other side. So QF test throws an error, the images don't match. What happened here for this flow diagram? It's an even size mismatch. Microsoft Edge shrinks the image a few pixels less, and QF test fails to verify this image. It's an error. If I zoom in a little bit, you can see Internet Explorer here is crispy sharp, whereas Microsoft Edge is a little bit blurry here. Okay, what to do? Before I give you some examples about our algorithms, I want to show another thing which might fail. No, sorry for the German word, however, it just tells automized GUI tests with QF test. I want to show you something which has been captured on Edge and replayed on Edge. On the same machine, same configuration, everything identical, but the images do not match. So where's the difference? If I zoom in here, You can see here on the expected image there's a reddish line here for 1 pixel, and on the right side there's a bluish line. Whereas at the got image, the bluish line is on the left and the red one is on the right. So what's the difference? The difference is the so-called clear type setting. Clear type is a feature of Microsoft Windows which allows font rendering to be more precise, to be more suitable for humans to read on a monitor, on a display. It depends on a system or user setting via the system control panel of Windows, and it also depends on the monitor and display driver of your operating system. So what could fail? For example, if you record your tests and you get a new display for your computer with a new driver, the default setting for clear type may change and your tests may fail just because of a new display. Okay, what to do? QFTest provides certain algorithms here to avoid these failings and to accept such little deviations in images. I'm now going to replay some image checks here to show you the outcome in the run log. All these images have been captured on Internet Explorer and now replayed on Edge. As you remember, the one which I have shown previously, it still fails, of course. The images still don't match. On the left, it's Internet Explorer. On the right, it's Microsoft Edge. Okay. The algorithms of QFTest can be defined here at the check image node using this attribute algorithm for image comparison. The syntax here is explained in our manual. You can simply right-click this attribute and select what's this, and then you will open the manual in your browser, and it directly jumps to the relevant part of the manual. Okay, in this case, I'm using the identity algorithm. What does it mean? QFTest tells the images still don't match, but now it tells there's an expected probability of 99% and a got probability of about 10%. So what does this algorithm do? I first want to show you these two buttons here on the left, the yellow one and the black one. If I click on the black one, QFTest shows for each pixel if the pixel is identical from expected to got image or if it's a difference. Here, each white pixel is different and each black pixel is identical. If you remember, these whites here are identical and the blues have all a slight variation of just a little bit. And the XOR button does even a color comparison, whereas you see those slight variations. So what does this algorithm do? It compares each pixel from the expected image and the got image, and it counts the identical pixels and the not identical pixels. In this case, about 10% are identical. As you can see here, blacks are identical and white pixels have a mismatch. So this algorithm is only good if you want to accept images where, for example, 95% of the pixels have to be identical and you don't care about the other 5%. In this case, it does not help. Now coming to the next one, the similarity algorithm. Actually, this is my personal favorite of all algorithms And whenever you don't know what algorithm to use, then you should simply use this one. In most cases, it's the best one to use. In this case, you can see the result is a GOT probability of over 99%. And that's what also a human may think about these images. So what does this algorithm do? Again, for each pixel, it compares the GOT pixel values against the expected values for the red, green, and blue channel of each pixel. And it tries to compare the color values. For example, a light blue is nearly identical to another light blue. And a dark blue would be a little bit identical or similar to a light blue. Whereas, for example, a red pixel is completely different to a blue pixel. And these combined probabilities together gives us a result here. So, for example, for each image where just the color variation is a little bit different, or the saturation is a little bit different, or anti-aliasing is a little bit different, this is the algorithm to use, the similarity algorithm. So now coming to a few more special algorithms. In most cases, you won't need these algorithms. For most cases, identity and similarity are the one to go. But I want to show you them anyway. The block algorithm. What does it do? It modifies the images and it creates these squares, which you can see here. Each square is calculated by the pixels which belong to the square. For example, a white square has many white pixels and a few others. As you can see, I switch back to this view here. You can see these squares here. And each square is then compared from the GOT image to the expected image. And again, the identical squares are counted against the whole square. There's a whole amount of squares. In this case, the probability is only a little bit above 1%, so still failing. So when to use this algorithm? For example, if you have an image where you allow, for example, 5 pixels to deviate and all other pixels have to be identical, but you want to have even a more sharper and crispier check than the identity. Remember, identity here is 10%. You can use this one. It goes down to only 1%. But it would accept, for example, just 5 deviating pixels. So coming to the next, the block similarity. Block similarity is a combination of block. So first it calculates these blocks, and then it does a similarity check for each block. Again, light bluish color is identical to another light bluish color, whereas a red color is not identical and not similar to a blue color. So in this case, it gives a very high probability. In most cases, the block similarity and similarity give nearly the same results. Now coming to the histogram, mostly used to compare real photographs. For example, to calculate if a photograph is similar to another photography. For example, a desert photograph is similar to another desert photograph because of many brown and yellow colors, but it's not similar to a forest, for example, where many green colors are there. So a histogram is just a calculation of color values and mostly only used for photographies. So now let's go to the discrete cosine transformation. It's a little bit hard to explain. So what does it do? A cosine function goes up and down with a certain amplitude. And if you don't view it from the side, but from the top, you can imagine an up is a light color, for example, a white, and a down is a dark color, for example, a dark or a dark blue. And if you now combine multiple cosine functions and add them, you can create an image which looks a little bit as the real image. In this case, you can see here the white in the middle, which comes just from one cosine function. Here on the top, it goes down, then up, and again down, the amplitude of the cosine function. And if I add more than one, for example, in this case 20, you can see the QFTest logo here is visible as a very, very blurry image. But if you would add even more cosine functions, it would go more and more to the real one. In most cases, this is used for very special image comparisons. And now combining the block algorithm with the discrete cosine transformation, you will get this one here. A side note, the image compression JPEG is based on a very similar technology. So the last one is a bilinear filter. In this case, the image is shrinked and then it is stretched again using a bilinear filter, and thus creating these blurry images. In most cases, only useful for very special image comparisons. So, summarizing this chapter here, in most cases you can use similarity or identity. Similarity if you accept color variations, and identity if you accept only a very few amount of deviating pixels. Okay, coming now to the next one. As you remember, this one which has been stretched or on the Microsoft Edge, you can use the algorithm called resize. It's defined here as a resize. In this case, the got image is resized to match the size of the expected image, and then a similarity comparison is done. In this case, these images are matching with 99% again. Okay, you could also do search for an image on another image. In this case, you can define the parameter find to look for a certain part of image. In this case, this icon here on the whole header of the web application here, and QFTest tries to find this image anywhere here on the header. And it was successful here on this part of the image, and even with 100% matching. Okay, now let's go to some scripting here. The most important class for scripting is the so-called image wrapper. You can use the image wrapper in any script in QFTest. And after you have initialized the instance here, you can do some very useful functions here. For example, grab an image of a component or grab the desktop screenshot. You can also load PNG files and save PNG files. in this case, I grab the image of the QFTest logo, stored in this local variable, and then I load an image from the file system here, and then I do an image check here from the one image with another image using this algorithm here. And this is the same as when you directly replay an image check. The image wrapper here is documented in our manual as well as this class here. Actually, that's an image wrap, an image representation, which is also documented in the manual and the whole app here too. So coming back to recording image checks. If I record this image here, I would always have to add an algorithm here. For example, for each of my image checks, I would have to add something like similarity expected. And if I have thousands of image checks, I would have to add this on all my image checks. For example, if I move from Internet Explorer to Edge, this would be a very unpleasant work. I could also use a variable, my algorithm here, if I want to be a little bit more on the safe side, if I have to add and modify the algorithms later on. However, it's still not fun to always add these things. So what to do? You can register a so-called custom checker. Custom checker allows to register certain checks for QFTest. The checks, which you can see here, are default checks of QFTest, but you can add whatever check you want using the custom checker API. For example, you could also add a check to verify a certain class attribute or similar attributes for web applications. In this case, here is my custom checker. It's about 90% of glue code to register a custom checker. And the important part here is, again, I'm initializing the image wrapper, and then I grab an image of the component, and then I directly set the algorithm to use. All other lines of the script is just glue code to register a custom checker. So now I have replayed and registered these checkers, and now I'm able to record an image with algorithm here. And if I record this check, it automatically gets a different identifier, and the algorithm is automatically set here. You could also register different custom checkers here and provide different algorithms here to directly record. It comes in very handy. For example, if one of your developer team implements these checkers, and all your testers and users of QFTest can simply record and replay them using this menu here, as they do not have to take care about anything or any code here. Okay, coming to a native checker. What is a native checker? For web applications, it's not necessary, but for Java applications or native Windows applications, it might be necessary. For example, if you have a Java applications with some kind of OpenGL hardware accelerated rendered 3D world or something like this, our QFTest internal mechanism might not be able to capture the images of this OpenGL rendered scenes. In this case, you have to register a custom checker. Again, much glue code here, and only 3 important lines of code here. What does this native checker do? It takes a screenshot, a real desktop screenshot, using methods directly from the operating system, and then it crops the image to the part here, and then it creates an image check data which can be later on used for the checks. So after registering this check, this one, I have another check here called native image. I can record it. This time it's a native image without algorithm, but it uses the operating system's functions to capture these images. This works in every case where our default image checks recordings do not work. As I said, for example, for OpenGL or similar hardware accelerated applications. Of course, you could also combine a native image checking and image grabbing with recording a custom algorithm here. So, coming now to the next chapter here, a little bit special. The previous chapters were all about capturing images and doing image checks with certain algorithms. Now we're coming to special cases and modifying and manipulating images. For example, in this case, I want to count the letter O here, but not using a textual method, but via an image check. I want to find this O and I want to count. And I can replay this. And it prints out 7. Okay, let's have a look to the run log. What does it do? Here at the very end, you can see the images don't match. So what has it done? Here on the right, you can see there are 7 black squares. Here, 1, 2, 3, 4, 5, 6, 7. No more O's to see. No. And this is marked E here. So QF has already found 7 O's here, and now it tries to find another O. And maybe this E here, it looks a little bit like an O, but only for 86%. So it's not good enough to be an O here, which I expected to be 92% identical to this O. Why not 100%? Because of anti-aliasing and clear typing, as you can see here. A little bit bluish on the left and a little bit reddish on the right. That's because of a different anti-aliasing and clear typing. If you zoom even more, you can see here the clear type, which I have mentioned earlier. So how does it work? Let's have a look at the script. Again, most important class, the image wrapper and the image wrap. Image wrapper is the helper class, which I have explained earlier, and image wrap is an internal representation of each image within QF-test. So what do? We have defined an algorithm here. We load a PNG from the file system. Then we create this black image which we will use later on. And now we grab the image of the component, in this case of this text here. So now we compare the whole image against the expected image of the O using an algorithm. And we use the find parameter to find the image. After we have found one of the O's, we modify the got image and copy the black square where the O is located. And now the loop continues to the next iteration, where QFTest tries to find the next O. And because of the first O has already been blacked with this black square, it will find another O. Or if there's no O present anymore, the check image advanced will stop with an exception here. The loop will end, and we have the final result. So let's have a look again at the run log. We found the first O here, matching with 100%. This O will now get a black square on it here. And we found the next O here, matching with 99%. Coming to the next one, it's blackished. Here with next OS has been found, and so on until the last one, where all 7 O's have been found, and only the E here is left, but the E is not good enough. Okay, so for example, the next thing here, we have now learned how to find images and count images on a larger image. Now we try to do to ignore some of the image parts. For example, I'm now replaying this image check of the whole header area here against Edge, and it works. There's no error because it has already been recorded on Edge here, so it's 100% identical. So what happens if I add some text here? Of course it will fail now. Not unexpected. Here it has search, here it has text. And as you can see here, these pixels do not match, so the whole image doesn't match. Of course, you could use an algorithm now, for example, similarity, and expect that maybe 89% should work, I think. Yeah, it works. But you do not know where the deviation is, these 2%. Is it here where text versus search, or is it here EN versus DE? So the image check is actually no use because you want to have a 100% identical image, but you do not care about this area here on top. Okay, for example, you could think about this one. Each pink pixel should be ignored because you do not care what there is. Of course, if you just replay this one, it will fail because many pink pixels against the real pixels are not identical. So it will fail. But using the script here, I get a successful check with 100%. Although the expected image, the got image is this one here, and the expected image is this one with the pink pixels here. So what does the script do? First, it grabs the image, again using the image wrapper. Then it loads some PNG from the file system. It's a mask PNG, which is this one here. And then it iterates over each pixel from the expected image, and where it finds this pink pixel, at this coordinates, it also sets the got pixels to this pink value. So you can modify the real red, green, blue values, RGB values, at the got images and at the expected image. And after that, you do an image check. And of course, it succeeds because the got image has been modified here before checking. Here we can see the expected images and got image both have these pink bars here now, the pink pixels, because they have been modified before doing the check via the script here. However, you should take care. For example, if you mask 50% of the image, so you say 50% of the image will be pink, then you will get an image check with a 50% success, independently of the other pixels, because pink always matches pink in this case. Okay, so one more special modification here and some very useful lines of script. For example, QFTest not only compares images, but it can also modify images, as you already have seen here. And you can even do more. The most important part is the QFTest image representation is a little bit tricky to modify. As you have seen here, you can get the RGB pixels as array and I can modify them. However, that's not very easy and it's not very understandable. However, you can convert a QFTest image representation to a Java buffered image with only 3 lines of code. And you can also convert it back, a buffered image, to a QFTest image representation. These lines are very helpful for each image manipulation you want to do with QFTest. Okay, what do I want to do here now? I want to have a look on all components of this web page, and wherever I can find a certain regular expression, a real text in this case, not via image comparison, but with a real text, I'm looking for this regular expression here where for each component which contains a small letter p. For example, in this case, it should be support, 2 p's here, and company has a p, solution does not have a p, and all components which QFTest finds should be highlighted, and the highlighted screenshot should then be logged to the run log. And as you can see here, it just did it, just ran against the header, not the whole site here. It doesn't care. However, support has been highlighted here and company has been highlighted. This is, for example, useful if you have a very large table or a list of persons, for example, a real huge database, and you want to find and you want to take a screenshot and highlight some parts. For example, if there is the word error anywhere on the screen, you want to highlight it in red. That's possible with this script here. So coming back to the script, what did it do? It grabbed the image from the component here using the image wrapper. Then it converted this image to a buffered image. And then it can use the graphics2D object instance of Java and do whatever this API of Java can do. For example, it can draw a rectangle, this kind, in this example, the red one. You could do any image manipulation what you want to do, and which Java provides here. And after you've finished your drawings, you convert it back to an image wrap, and then you can simply log it to the run log. Okay, so what did we learn today? We saw the problems and issues of image checks. For example, when you have recorded image checks on Internet Explorer and you want to replay it on Microsoft Edge or any other browser. You have seen the special cases for anti-aliasing and font rendering with clear typing. You have seen some algorithms and when to use them. Most important, again, similarity. And you have seen how to register custom checkers. Not only important for image checks, but for any other check you want to do, and which comes not out of the box with QF test. And you have seen some special things you can do with QF test here and the images, for example, count images, and you have seen how to modify images, draw images, and of course, an important part, to ignore certain part of images. So thank you very much for your attention. I wish you a nice week and stay healthy, and thank you very much.